Okay, let's just jump right into this explainer. Today, we're embarking on a journey to the very center of matter. We're looking at a true scientific detective story that completely changed our entire view of the universe. We're going to uncover the mind-bending, almost terrifying paradoxes hidden inside literally every single object you touch. We'll trace the incredible journey of how scientists figured out what an atom actually looks like, even though they couldn't even see it.
I mean, think about the solid ground beneath your feet, or the device you're watching this on right now. It feels completely solid, right? But what if I told you it is almost entirely composed of nothingness? Seriously. If atoms make up everything in the universe, why is everything mostly empty space? It's a huge mystery, and to understand how we solved it, we kind of need to rewind the clock to a time before we actually understood the inner workings of the atomic world.
Which brings us to Section 1, the plum pudding illusion.
So, by the late 19th century, scientists pretty much agreed that matter was made of atoms. But then, in 1897, English physicist J.J. Thomson makes this massive breakthrough. He discovers that atoms contain these identical, negatively charged little things called electrons. Now, since atoms as a whole are electrically neutral, Thomson knew there had to be a positive charge in there somewhere to balance it all out. But how was it arranged? Well, in 1898, he proposed our very first atomic model. He hypothesized that the positive charge was just uniformly spread out through the whole volume of the atom, and the negative electrons were stuck inside it, kind of like seeds in a watermelon. People affectionately called this the plum pudding model. It was neat, it was comfortable, and it honestly made perfect intuitive sense. That is, until the physical data came in and proved it completely, undeniably wrong.
And that leads us to Section 2, firing a gold foil.
The undoing of that plum pudding idea started with Ernst Rutherford, who actually used to be Thomson's student. In 1911, Rutherford's team, specifically Hans Geiger and a 20-year-old undergrad named Ernst Marsden, set up this incredibly ambitious experiment. Picture this. They fired a tightly focused beam of high-energy alpha particles at a ridiculously thin piece of gold foil. We're talking just over 2/10,000,000ths of a meter thick. These alpha particles are positively charged helium nuclei, blasting out of a radioactive source at a massive 5.5 mega-electron volts. They set up a rotatable detector with a zinc sulfide screen to catch the tiny flashes of light whenever a particle hit it. Now, based on Thomson's watermelon model, the positive charge in those gold atoms was supposed to be so spread out that these heavy, super-fast alpha particles should have just blasted straight through with basically zero deviation.
And, most of the particles did pass right through. But then came the twist. They noticed that a tiny fraction, about 0.14%, scattered by more than 1 degree. And even crazier, about 1 in 8,000 particles deflected violently by more than 90 degrees. They literally bounced straight back toward the source. Rutherford later said it was as incredible as if you fired a 15-inch naval artillery shell at a piece of tissue paper and it came right back and hit you. No way around it, the plum pudding illusion was officially shattered.
Which kicks off Section 3. The empty space atom.
So Rutherford looks at this data and realizes this violent backwards deflection meant the incoming alpha particle must have slammed into an incredibly intense electric field. For that to even be possible, almost all of the atom's mass and all of its positive charge had to be tightly packed into a tiny, tiny central volume, the nucleus. To give you an idea of the scale here, his math showed the nucleus has a radius of somewhere around 10 to the negative 15 meters, but the entire atom was known to be about 10 to the negative 10 meters. Put simply, the atom as a whole is 10,000 to 100,000 times larger than its own nucleus. The electrons are just way, way out there orbiting at massive distances. To really wrap our heads around this, let's scale it up. Imagine the nucleus is the size of our sun. Where would the electron be? Well, if the solar system had the exact same proportions as an atom, the Earth wouldn't be where it is now. It would be over 100 times farther away from the sun than it actually is. It's wild to think about, but an atom contains a much greater fraction of completely empty space than our own solar system does.
Now, what happens in that empty space all comes down to what physicists call the impact parameter. That's just the distance between the alpha particle's incoming path and the dead center of the nucleus. Since the atom is mostly empty, a large impact parameter means the particle sails right through, no problem. But a small impact parameter, that's a near miss, or a head-on collision with that incredibly dense little nucleus. And that is exactly what causes the massive electrostatic pushback that sent that 1 in 8,000 alpha particle ricocheting backward.
Moving on to Section 4, the spiraling electron crisis.
Okay, so Rutherford's planetary model was a huge leap forward. We've got a tiny, dense, positive nucleus with electrons orbiting it like planets around a sun, all held together by electrostatic attraction. But there was a fatal flaw hiding in this beautiful picture, and it came from the unbreakable rules of classical electromagnetism. It sparked a terrifying question that threw all of physics into a total crisis. If electrons are orbiting the nucleus, why don't they just crash right into it?
Here's the problem. According to classical physics, because an orbiting electron is constantly changing direction, it's technically always accelerating. And an accelerating charged particle must continuously emit electromagnetic waves, which means it is constantly losing energy. If it's losing energy, its orbit has to shrink. It should spiral rapidly inward and just crash right into the nucleus. If classical physics was totally right, matter as we know it literally could not exist. Atoms would instantly collapse. Plus, as they spiraled in, the changing speed would produce a continuous rainbow of light, which totally contradicted the very specific, distinct lines of light that chemists were actually seeing in their labs.
Enter Section 5, Bohr's Quantum Leap.
In 1913, Danish physicist Niels Bohr showed up at Rutherford's lab and realized they needed to break the old rules to save the atom. He brilliantly mashed up the classical planetary model with the brand new quantum theory from Max Planck and Albert Einstein. He came up with 3 revolutionary steps. Step 1, he just boldly declared that an electron can revolve in certain stable orbits without emitting any energy at all. Just boom, classical rule broken. Step 2, he defined these orbits by saying angular momentum is quantized, meaning it has to be a strict integer multiple of Planck's constant divided by 2 pi, no in-betweens. Step 3, he said radiation is only emitted when an electron jumps from a higher energy orbit down to a lower one. The photon it shoots out has an energy exactly equal to the difference between those 2 states.
These postulates mapped out highly specific energy levels for the hydrogen atom. The lowest level, where the electron hangs out most of the time, is the ground state, sitting at negative 13.6 electron volts. That negative sign just means the electron is trapped, bound to the nucleus. If you want to completely rip that electron away and ionize the atom, you have to hit it with exactly 13.6 electron volts of energy. Hit it with a specific smaller amount, say 10.2 electron volts, and you just excite it, bumping the electron up into the next energy level.
Let's look at Section 6, Decoding Atomic Fingerprints.
So Bohr's idea of these quantum jumps perfectly explained the forensic evidence scientists had been stuck on for decades: atomic spectra. When you run an electric current through a gas, it doesn't glow with a continuous rainbow. It creates an emission spectrum, very specific, bright, sharp lines on a totally dark background. On the flip side, if you shine white light through a gas, you get an absorption spectrum, which is a full rainbow missing specific dark lines. And those dark lines, they match the bright lines of the emission spectrum perfectly. These exact wavelengths act as a literal, unique atomic fingerprint for every single element in existence. For years, scientists like Johann Balmer had these math formulas that predicted exactly where hydrogen's emission lines would show up, but nobody had a clue why the math worked. Bohr's quantum model was the key. Those bright lines you see in a hydrogen spectrum, they are the actual, visible flashes of light shot out when an excited electron falls from a higher quantum orbit back down to a lower one. The atom is releasing a photon with a precise, mathematically predictable frequency.
It was a total triumph. Bohr won the Nobel Prize in 1922 because he gave us the rule book for the atom and explained why matter doesn't just collapse into nothingness. But it left one absolutely massive question hanging. Why do these rules exist? Why is an electron forced into these rigid, quantized orbits in the first place? 10 years later, in 1923, a French physicist named Louis de Broglie would suggest an answer even crazier than Rutherford or Bohr. What if the electron isn't just a tiny planet orbiting a sun? What if, somehow, it's actually behaving like a wave? Well, that wave-particle duality is a whole other quantum mystery, and we'll have to save that for next time. Thanks for joining me on this explainer, and I'll see you in the next one.